Okay. Before I start the session for today, are there any questions that you want me to answer with regard to the subject matter so far? Wala bang mga tanong? Everything okay? I hope. Okay, I expected you to have at least gone through the material, the initial material for Module 2. So we're moving into a new module this week, Module 2. This is a review of basic semiconductor devices. So in this particular module, we're going to review the diode, the bipolar junction transistor, and the MOSFET. And we're also going to have a section in this module of the op-amp, which is already considered a basic building block in electrical and electronics engineering. So I expected you to have gone through the notes already and possibly even recording. So I'm not going to repeat the lecture that I already recorded for this particular module. No, I'm the handler in charge of this module. I'm just going to go through some of the material with you. Okay, let's start. Let me share my screen. Okay, so in this part of the course, we're going to start with an exponential. We're going to start with the exponential and small signal models of the diode. So there's a part one. Yung part one is really just a review of what you already took up in EEE 123. These are the linear piecewise models of the diode and the diode circuit analysis. Kinuha na niyo yan sa 123. That's why there is no recorded video for that particular part. So just go through it again, just to review the basics of the diode. So we're going to start with the exponential and small signal models of the diode. Okay, so this is the exponential model of the diode. This is based on Shockley's equation. So this okay, so this is based on Shockley's equation. We did not go through the derivation of Shockley's equation, but because the diode in the forward bias region is actually diffusing, then there's a exponential profile of minority carriers being injected in the P side and in the N side. There's a exponential profile, no? And that's the reason why we come up with an exponential relationship. Okay, so ID is equal to I of S e to the VD over eta VT minus 1. Where we said that I of S is your reverse saturation current. This is a very small number, anywhere from 10 to the minus 9 to 10 to the minus 15. V of D is the voltage across the diode. So ang reference, this is the reference, no? This is V of D, and this is I of D. So V of D is the voltage across the diode. V of T is your thermal voltage. Okay, this is KT over Q, where K is Boltzmann's constant, T is your temperature in degrees Kelvin, Q is the charge, the equivalent charge of one electron. This is approximately equal to T over 11,600. So if you want to compute for V of T, depending on the temperature, you can approximate that by T over 11,600. Then yung eta natin, this is your ideality factor. Okay. This is a function of how well the diode is is manufactured, and usually we say this is equal to 1. Usually equal to 1. It's equal to 1 for a well-manufactured diode, and it is usually a well-manufactured diode, especially when the diode is in an integrated circuit. Now, under normal, okay, so when it is forward biased, means V sub D is positive, no? So forward biased, okay, ang ibig sabihin nito is V sub D is greater than 0. That is the anode. So if you remember the terminology in 1, 2, 3, you call this the anode, you call this the cathode. The anode is positive with respect to the cathode, no? So forward bias, that's V sub D is greater than 0. If it is reverse biased, it's V sub D is less than 0. Okay, under normal forward bias, okay, E to the V sub D over eta V sub T will usually be very much greater than 1. No? And if you, for example, let's say V sub D is equal to 0.3 volts. And 0.3 volts is less. Note that this is even less than the cut-in voltage in the piecewise linear model. In the piecewise linear model. Okay, I should emphasize that this is not a linear model because this is not a linear equation. So ano yung cut-in voltage sa piecewise linear model? Just so I know that you're still keeping up. What is the cut-in voltage if this is silicon?
0.7, sir.
That's right. No, it's 0.7. So this is even less than the cut-in voltage. So according to our piecewise linear model, the current will be equal to 0. It will be non-conducting because it is very small. But actually, there will be a very, very small current, almost negligible current. If I compute for e to the Vd over nVt, assuming n is equal to 1, e to the Vd over nVt, this is, and I computed this already, this is 102,386. So ano ba naman yung 1, itong 1, compared to this? No? That's why under normal conditions, under normal forward bias, we usually just say I sub D is approximately equal to I sub S e to the Vd over n V sub T. In other words, we just disregard this one. On the other hand, under usual reverse bias, because usually when you reverse bias a diode, you reverse bias it by a few volts. So under normal reverse bias, okay, e to the Vd over nVt is approximately equal to 0. You imagine a negative value of V sub D. Because kung reverse bias, that means itong V sub D is negative. If you try to compute this is going to be approximately equal to 0. And therefore, I sub D will just be minus I sub S. So if you reverse bias a diode, let's say this is your voltage, and then you reverse bias a diode, okay, you are going to get a current flowing, but that current will be I sub S, a very, very small amount of current. What is that? That's somewhere from the nanoampere range to the femtoampere range. No? Nano 10 to the minus 9, femto 10 to the minus, yeah. femto 10 to the minus 15. Okay, having done that, let's do this. Now, why don't you try solving this problem? So the answer to this problem is in your notes. So please don't look at the notes. I just want you to practice solving this problem. So I'll give you 5 minutes. No? So a diode has Is of S equal to 10 to the minus 14 amperes. Okay, this is 10 femtofarads. Ideality factor of 1 at 27 degrees. What is the voltage across the diode if the current through the diode is 10 milliamperes? So if you have your calculators, please type an answer in the chat box as soon as you get an answer. So I'd also like to know who are trying to keep up with the course among those that attended. So paki-sagot lang. Give you 5 minutes, no? Because this is something that you should be able to solve in maybe just even 2 or 3 minutes. Okay, so I have an answer already, I hope. Let's wait for a few more answers. Isa pa lang yung nakakasagot.
Sir. Yeah.
Okay, I have thank you very much for those that tried, no? Tatlo lang, no? Maybe in the next question more people can answer. Okay, the first two answers that I got, 0.718, 0.72, those are both correct. Thank you very much, Jarrod, for trying. So yeah, how do you solve this problem, no? Well, sinabi ko na, no, na Is of D for this particular case, you have Is of D is approximately equal to Is of S e to the Vd over eta v sub t. So you can actually solve for v sub d. V sub d is equal to eta v sub t ln of I sub t over I sub s. And then we said that eta is equal to 1. Is equal to 1. V sub t is 0.026. You have ln of 10 times 10 to the minus 3 over 10 to the minus 14. And if you solve this, it's going to be equal to 0.718. Okay, I want you to do the same thing this time for 50 MA. Okay, so andyan na yung mga formula, no? Do the same thing for 50 MA. Ma-practice lang kayo sa calculator ninyo.
Sir, ask ko lang, ba't hindi siya sinubtract sa 1 po?
Yeah. Did you miss the first part of what I said earlier? Na under normal circumstances, itong e to the vd over eta vt will be very, very much greater than 1. So nagiging negligible yung 1.
Okay, sir. Baka nakalimutan lang. Thank you, sir. Thank you, sir.
Yeah, sure. No problem. No. Otherwise, kung ilalagay mo yung 1 dito, you're not going to be able to solve for v sub d in terms of I sub d. Kahit anong gawin mong manipulation, hindi mo magagawa. Although magagawa ng calculator mo using the solve function. Okay, I already have a few answers, So that's right, So the answer is 0.76. So by substitution into the same formula, dito sa 50 MA, v sub d is equal to 0.76. Okay. So what I want to emphasize here is that yung current natin nagbago by 5 times. Our current increased by 5 times from 10 MA naging 50 MA. But if you take a look at the voltage from 0.718 to 0.76, 0.05 or 500ths lang of a volt ang nagbago. That's because we're already operating in this particular region, where this is approximately equal to 0.7. So even if you have a very large increase in current, your diode voltage does not increase that much. Okay, so this is I sub d versus v sub d, and that's what justifies the piecewise linear model of the diode. Kung naalala niyo yung piecewise linear model ng diode, okay, we approximate the diode. We approximate the diode this way. This is the second approximation. The diode is approximated as a constant voltage source. And then the third approximation, the first approximation is ideal. Second approximation is this approximation. And then the third approximation, lalagyan lang natin ng konting slope. Yung third approximation natin, if you recall the third approximation, it's something like this. Yun naman yung third approximation na may konting slope. Okay, are there any questions? Okay, this problem is a little bit more difficult. The circuit shown employs 2 identical silicon diodes. Okay, assume the temperature is 27 degrees centigrade. Use the exponential model to determine the voltage across each diode if the ideality factor is equal to 1. Okay. Question. What will be the value of the current that will flow? you have two diodes that are back to back. You have two diodes that are back to back. If this were ideal diodes, what current would flow? Can somebody shout out an answer? If this were ideal diodes.
Zero, sir.
That's right, no? If this were ideal diodes, zero current will flow. Kasi, okay, what is an ideal diode? An ideal diode supports the flow of current in only one direction. So maybe, okay, you have this supply voltage. This supply voltage is trying to push current to flow in the clockwise direction. So maybe this will support the flow of current, but because this is connected in series opposing, it is going to reject the flow of current, and therefore, if these were ideal diodes, I of these equal to 0. Now, them being not ideal, what do you think the value of I of D is going to be? Anyone? It being not ideal. Hindi siya 0, no? It's not going to be 0. What will it be? Any guess? Challenging you to guess. Educated guess, ha? Wag hula-hula lang. Educated guess.
I sub S.
That's a very good guess, no? Ang magiging value ng I of D, I of D will be equal to I of S, the reverse saturation current. Why? Okay. Okay, assuming you have a current that is flowing clockwise. One will be forward biased, the other will be reverse biased. The forward biased diode is going to have a small voltage across it. Maliit na voltage, yung magiging voltage dito sa forward biased diode. Therefore, the voltage across your reverse biased diode is going to be relatively large compared to the voltage across the forward biased diode. As a matter of fact, most of these 5 volts pupunta dun sa reverse biasing the second diode. And as we mentioned here, okay, under normal reverse bias, I of D is equal to negative I of S. No? So why negative? No? Bakit dito I'm saying positive? Well, because the direction of flow of current here in this diode, the direction of flow of current is opposite the reference direction. Remember, our reference direction is this way. Okay, this is I of T, and this is B of T. But if you notice, it is opposite the reference direction. That's why it becomes positive. Okay. So, having said that, okay, what will be okay? Okay, for D1, for D1. First of all, now I cannot assume. Okay, let me write this equation. This is I of S e to the V of D over NVT minus 1. I cannot assume now that this is going to be much greater than this. Di ko pwedeng i-assume yon. Okay. And the reason for that is the current that is flowing is very, very small. And therefore, if I have a voltage across this, that voltage can be quite small. No? So I cannot assume that this will be much greater than this. So I'm going to have to use the full Shockley equation. Okay, but what is I of D? We already said that I of D is equal to I of S. Right? So this is actually equal to I of S. Or e to the V of D over NVT minus 1 is equal to 1. Okay? Kasi magka-cancel out tong I of S na to. E to the VD over N V of T will be equal to 2. Okay. Eta is equal to 1. V of T is equal to 0.026 volts. Okay. You can solve for VD. And if you solve for VD, okay, you're going to get VD, V1, no? Sorry, sorry about that. Okay. This should be V1. So if I solve for V1, I'm going to get V1 is equal to 0.018 volts. So see that it is very, very small, 0.018 volts. Yun yung voltage dito. That is the voltage across D1 if the current, the forward current is I of S. So knowing now V1, what is V2? Siguro naman kaya na nyo yan, ano? What is the value of V2, knowing V1? Anyone? Okay, that's right. Huh? It's just going to be 4.982 to be exact, no? If this is a V1. How do you get that? You just get that using KVL. Because 5 volts minus V1 should be equal to V2. So V2 will be equal to 4.982 volts. Any questions? Of course, this is all very ideal, because the Shakti equation is an idealized equation. It assumes that all of the physics works perfectly in the diode. It's an idealized equation. I'm not saying this is an ideal diode. I'm saying that Shakti's equation is an idealized equation. Are there any questions? Okay, let's move on to the next model which we're going to use. This particular model, just so I know, there's a question. Okay, yeah, there was a question, no? By the way, no, there's a chance I already told the class this, there's a chance I might not see your question in the chat box. It's better if you interrupt me. Okay, so yung tanong is, bakit hindi negative IS yung current, no? The reason why hindi negative IS yung current, if you take a look at diode D2, so let me just draw diode D2. This is V2, okay? And then this is I of D. But if you take a look at the usual convention, okay, okay, it should be I of D should be this way. I of D should be this way. Okay. Actually, this is going to come out negative, no? Because this is V sub D. So this is going to come out negative. Okay. But I of D is also going to be negative. Kasi dapat ganito yung direction ng current. And that's why I of D will be equal to I of S. Okay. So I was starting to say we'll move on to the next model of the diode, and this is the small signal model of the diode. But before doing that, I'm going to give you a short introduction into small signal versus large signal. So normally in electronics we have the large signal model and we have the small signal model. What are the differences between the two? So your large signal model, this is used over a large range of voltages or currents. So ang large signal model mo, yung mga voltahe natin or yung current natin can swing very large values. On the other hand, yung small signal model, the voltages or currents are restricted to very small variations. Kung magbabago yung voltage or current natin, maliit na maliit yung magiging variation. Now, for semiconductor devices, the large signal model is typically exponential or polynomial. So nakita na natin yung diode. If we're not using the piecewise linear model of the diode, if we're using the Shockley model, the equation is exponential. You also learned in EEE 123 that for a MOS transistor, your model is polynomial. You remember in saturation, your drain current is proportional to VGS minus VTH quantity squared. No, that's a polynomial. If your equation is exponential or polynomial, those are nonlinear equations. Okay, on the other hand, pag small signal, the device is considered linear over the signal range and can be modeled using linear elements. So here, we cannot model the device using linear elements. But here you can, ano? Sariling, yeah. Okay, so for the large signal model, it's difficult to perform circuit analysis. You're going to usually have to do an iteration or use the solve function of your calculator. Whereas for the small signal model, nakita na natin in EEE 123 that we can apply nodal analysis, we can apply circuit simplification, we can apply the phasor method. You can use these tools for linear circuit analysis. Okay, so the large signal model, this is used in determining the DC operating point. You can use this to determine transfer characteristics. You can use this for low frequency analysis. On the other hand, the small signal model, you can use that to determine the parameters of your amplifier. Gain, input and output impedance, frequency response. So those are the distinctions between small signal and large signal. But the important distinction is the first. The large signal model, malaki yung variation natin sa voltage or current. Sa small signal, maliit lang. Okay, how do we determine the response? Yes, somebody raised a hand.
Sir, if I may ask, like,
Please. Go ahead.
so large signal does that mean like sine waves with like large amplitudes or
That's
something?
pag sine wave na malaki ang amplitude, hindi na yung small signal. Large signal yun.
So
Pag
like,
sine wave na maliit yung amplitude, that's small signal.
is there like a certain threshold na parang alam ko?
It depends on the device, no? It depends on the characteristics of the device. But rule of thumb, no? Just general rule of thumb. Sa electronics, sinasabi nating small signal pag yung variation is in the milliamperes or millivolt range. But that's just a very how do you say it? A very broad rule of thumb, no?
Okay, thank you, sir.
Okay. So how do we determine the circuit response? No? You will find out in the circuits that we're going to study in the future. When you have a signal, usually you can break that up into two components. You have what is called the DC component, and you have what is called the time varying component. So just to give an example, so this is a signal with a time varying component. So the signal is not steady DC. It is not steady DC. It changes in value. And in this particular case, I just showed a sinusoidal variation. Sorry, but my PowerPoint seems to have a mind of its own. It's advancing on its own. Give me a few seconds. Give me a minute. I'm going to try to fix it. No, sandali lang. Okay, I hope that fixed it. No? Okay, so here's an example. No? So I have a signal. This is a voltage signal. I call the voltage signal V in. Okay, and that signal is not a constant voltage. No? It is time varying. And in this particular case, I showed a sinusoidal time varying signal. But note that this has a DC component. No? In other words, if this is a sinusoid, it was translated upward. It is not symmetrical with respect to the x-axis. It was translated upward. So there's a DC component. So my DC component, that is this, capital V, capital IN. And then this is my time varying component. It does not have to be sinusoidal. I'm just showing here sinusoidal. And that is small v, small in. And my total signal, V in, is the capital V, capital IN plus small v, small in. So this is very typical of the types of signals that we see in electronic devices. So how do we analyze a circuit that has this type of input signal? We apply the principle of superposition. So if you recall the principle of superposition, the total response of a linear circuit is composed of the response of the different sources in the circuit acting alone. So we can consider this to be two sources in series. So the total response will be the response of the sum of the individual responses of the sources acting alone. So you get this source acting alone, this source acting alone. You add the individual responses and you get the total response. No? The total response is the response to the DC component plus the response to the time varying component. So I hope you still remember the principle of superposition. Now I just want to explain the conventions on notation. So this is quite important. Depending on the case, that is uppercase or lowercase, of either the variable or the subscript, you should have an idea of what component we are talking about. For example, ito, no? V in equal to capital V, capital IN plus small v, small in. Okay, V, let's say V, lowercase in V in, indicates that that quantity is a time varying quantity. Every time your variable is lowercase, then in general, that's a time varying quantity. Yung in, uppercase, dito naman sa V in, indicates that this is a total signal. That V in is a total signal. Yung in, lowercase, dito sa V in, sa small v, small in, indicates that this is the time varying component of small v, capital IN. And finally, whenever we have uppercase variables, anytime you have an uppercase variable, that indicates that that variable is DC. It does not vary with time. So this V uppercase in this V capital IN indicates that that is the DC component of V in. Okay. Are there any questions with respect to this convention? So the thing here is be careful in the case that you use for both the variable and the subscripts. Depending on the case, then you get an idea what that particular variable is. So for example, let me test you, no? And again, just shout out an answer. What if, okay, what if I have the variable I, small in? Anong ibig sabihin yan? Can someone tell me what that is? Anyone? I'll call out people at random. So pasensya.
Sir,
Hello.
is it that the current will vary with time? It's the current quantity will value with the current in quantity varies with time.
Yeah. First of all, the quantity itself is time varying. No? That means this quantity itself is time varying. That's a lowercase I. But what is the significance of the lowercase in?
Oh, sorry, is it the current signal at a given point in time, sir? Sorry.
No. You're talking about instantaneous values, no? I'm talking about a variable in general. No?
Oh, okay.
Okay. Yeah. When I say small I n, okay, that means this is the time varying component of I capital IN. No? It's a time varying component of I capital IN. No? And when you have I capital IN, that sort of says that this is a total signal. Total signal. That it has a DC component, and it also has a time varying component. Now, what will the DC component of this be? Can someone tell me?
Sir, capital I, tapos capital IN po.
That's right, no? So the DC component of this will be capital I, capital IN. No? This is the DC component of I, capital IN. Right? So that means my current I, small in, okay, is equal to I, capital I, capital IN, plus I, small in. Okay. So that's the conventional notation. Anyway, those of you that are confused, try to digest it some more, no? When you review the notes. Okay, so we have what we call large signal versus small signal analysis. So I started to talk about that earlier, no? So where did I talk about that? I said when we use the principle of superposition, the total response is the response to the DC component plus the response to the time varying component. The response to the DC component, we usually use large signal analysis. And the response to the time varying component, usually we use what is called small signal analysis. So that's the difference between large signal and small signal analysis. So for example, no, this is a diode. I apply a DC voltage in series with a AC source. So if I take a look at the total voltage across the diode, so this is my total voltage across the diode. So notice my my subscript, no? Small v capital D. The total voltage across the diode will just be equal to this plus this. So I'm applying the voltage across my diode. I'm applying a DC voltage plus a time varying voltage, and I should expect this current. I should expect this current to also have a DC voltage plus a time varying voltage. I mean, it's just natural that is what is going to happen. Okay, what does my okay, what does this establish? So remember, I can use superposition. Itong V sub D will establish what we call the operating point. Sorry. Okay, this V sub D will establish what we call my operating point. So if I take a look at the diode characteristic curve, so let me draw the diode characteristic curve here. Okay, so we know that this is exponential in nature. This is I sub d versus V sub d. This is my, let me use a different color. So this is going to be my diode characteristic curve. Okay. Okay. If I take a look, what is this going to establish? This is going to establish the operating point. So let's say this is V sub d. Let's say this is V sub d. That is going to establish my I sub d. This V sub d will establish this I sub d. Okay, what will this small v sub d do? No? This small v sub d will cause my operating point to shift up and down. No? To shift up and down. So if you take a look at the effect of your small v sub d, okay, it's going to be operating somewhere here. No? In other words, this is now my small v sub d. This is my small v sub d. And this is now going to be my small I sub d. This is going to be my small I sub d. Sorry, this is supposed to be d. Did you get it? Nakuha nyo? So itong capital V sub d will establish capital I sub d. And as this oscillates, okay, my operating point will be shifting up and down here. So as this changes this way, this is going to change this way. That is in time. So this is going to be my small v sub d, and this is going to be my small I sub d. Are there any questions? So I sub d is determined from V sub d using large signal analysis, and then small I small d is determined from small v small d using small signal analysis. Okay, what is the small signal diode module? If the amplitude of V sub d is small, so ito no, itong V sub d, if this is small, then if we take a look at the diode characteristic curve in this particular area, we can approximate that with a line, with a straight line. In other words, if I blow this, yes, here this is actually a curve, but between this point and this point, I can approximate it with the blue line. And that blue line has a slope which is 1 over r sub d. Small r, small d. That is the slope of the blue line. So what I can do is, instead of using the diode characteristic curve here, I can just use this blue line. In which case, we say the diode can be now, because this is a straight line, that is a straight line, the diode can be represented by a resistor R sub d. Okay, this resistance is not the same as, because some students get confused. No, they think that this resistance is the same as the diode forward resistance in the piecewise linear model. No, it's not the same. It might be close in value to it, but it is not the same. Okay, the value of this R sub d changes depending on where your operating point is. Because if my operating point, for example, were somewhere here, then the slope of my line here would be different from the slope of my line here. So the value of R sub d changes with your operating point. But the important takeaway from this is that your diode can be represented by a resistor. And you can determine the value of R sub d, by getting the partial of this expression. So this is Shockley's equation. If I get the partial of this expression with respect to V sub t, that is actually equal to G sub d, which is 1 over R sub d. Okay. Because remember, this is my expression for I. If I get the partial of I with respect to V, okay, change in I with respect to V is actually change in conductance, which is equal to the reciprocal of the change in resistance. So this is actually an expression for conductance at the point, which is the reciprocal of my resistance. So if I assume that V sub d is a normal value of V sub d, this one becomes negligible. So we explained that earlier. So this is my expression. If I try to get the derivative now of this with respect to V sub d, this is what I'm going to get. Oh, sorry, this is what I'm going to get. But notice that I sub s e to the Vd over eta Vt is equal to I sub d. So if I get this is just equal to your diode current. So my conductance is this. Now I have to evaluate that at V sub d equal to V sub d. So I evaluate that at this point. Okay. And this is what I get finally. Okay. Eta V sub t over I sub d evaluated at, because evaluated at this point, that is evaluated at I sub d. I sub d is the current at V sub d equal to capital V sub t. Are there any questions? So this is the important result. Okay, note that again, no? So this is just a note. RD is dependent on the value of I sub d. I already mentioned that. No? Depending on where you are in this curve, your slope changes, and therefore R sub d changes. Okay, so here's another example. The diode is silicon with eta equal to 1, Is equal to 10 to the minus 15. The circuit is operating at 27 degrees centigrade. So I have my excitation is a DC source in series with an AC source. The DC source is 0.8 volts. My AC source is a 1 kilohertz sinusoid whose RMS voltage is 5 millivolts. So earlier there was a question: can this be considered small signal? Well, 5 millivolts more or less would be small signal from the point of view of, from the perspective of a diode, because in the diode, if you get the variation of 5 millivolts, then you can approximate the diode characteristic curve to be a straight line for that variation. Okay, then you're given R 50 ohms, C 10 microfarads. So the question is, obtain a time domain expression for this current I sub x at steady state. And the solution to this, since my excitation has both a DC and a time varying component, I expect my response, so this is my response, this is what I'm trying to compute for, small I capital X, will also have a DC and a time varying component. So offhand I can already write, no? My small I capital X will be capital I capital X plus small I small x. So my response will have a DC and a time varying component. Okay. Sorry. Okay, to determine the DC component, we consider V sub x acting alone. So you learned in 1, 2, 3. If I wanted to consider this acting alone, what am I going to do to this? You remember? Pag superposition, no? Anong gagawin ko dito sa small v, small x ko? If I want capital V, capital X to act alone. Anyone?
Siya short. Oh.
Yes, that's right. Ano? So if I want this to act alone, I replace this with a short circuit. Okay. Now the other thing is this. At steady state, what is a capacitor equivalent to for DC? Do you remember? If you're taking up 1338, you would have been refreshed on this, no? So if you have a capacitor and you have a DC circuit at steady state, what is the capacitor equivalent to?
Open circuit.
That's right, no? An open circuit. Okay. So if I'm considering this acting alone, so this is a short, this is an open, ito na lang yung matitira. That is what will be left. Okay, I'll just have my DC source, my 50 ohm resistor, and my diode. Okay, I'm doing now large signal analysis. I have to compute for i's of x, capital I, capital X. Now, how do I do that? Two ways. One is you can, if you want to do an approximation, pwede, no? You can use the piecewise linear model of the diode. So pag ginamitan ko ng piecewise linear model ng diode, what is the value of i's of x? Can somebody tell me? Let's assume the diode is silicon. What will be the value of i's of x? Anyone? Okay, if I were using the piecewise linear model of the diode, and I just assume that this is silicon, I will assume that this is just 0.7 volts, right? And therefore, i's of x will be 0.8 minus 0.7 divided by 50 ohms. Okay, I don't know if people answered that. Yeah, no, tama ba? 0.1 over 50. 0.1 over 50. That's right, no? Okay. However, I can also use the Shockley equation if I wanted a more accurate determination of i's of x, no? So, for example, using okay, I have two equations. You have two equations in two unknowns. So the first is v of x minus v of d over 50 is equal to i's of x, right? So this is what I was saying earlier, that if you were using the piecewise linear model, you might just approximate v of d to be 0.7 if you know that the diode is silicon, and then you can right away come up with i's of x, no? But since here we were given the parameters of the diode, the Shockley parameters, then it's implied you should use Shockley's equation. So you have eta equal to 1, you have i's of s operating at 27 degrees centigrade. Okay, so this is your first equation. And what is your second equation? Your second equation would be i's of x is equal to E raised to the VD over N V of t minus 1. Sorry, i's of s. Okay, that's your second equation. Okay, so here I have 0.8 minus VD over 50 is equal to i's of x. That's my first equation. Dito naman, I have i's of x is equal to 10 to the minus 15, E to the VD, and then eta is equal to 1. Your temperature is 27 degrees centigrade, so that's this is going to be 0.026 volts minus 1. Two equations, two unknowns. How do you solve this?
So if I'm not mistaken, systems of equations po ba?
Yeah, definitely system of equations siya, no? Two equations, two unknowns. Pero ano yung paano sinosolve yung system of equation na yon? Ikaw, kung binigay ko sa iyo itong dalawang equation, how would you solve it?
Sir, substitution.
Hindi madali i-solve, di ba? And that's precisely the point, no? That's why it's not nice to do large signal analysis, because usually your equations are nonlinear. But you're very lucky because you have the solve function of your calculator, right? In other words, you just, for example, you just equate these two. If you equate this to this, you plug that into your calculator, you can get V sub D, and then after getting V sub D, you just get I sub X. No? So I'm just going to say, using the solve function of your calculator, you can come up with a solution. Okay. And what is the answer going to be? I'll just give you the answer. No, you're going to get I sub X is 1.44 MA. Okay. Earlier, people said 2 MA. That is if we just assume that V sub D was 0.7. No? So supposedly, if your Shockley model were accurate, this is supposed to be more accurate. Okay? Okay, so tapos na yung first part, no? Getting the DC component. Now, how do you get the time varying component? Okay, to determine the time varying component, this is small I, small x. We consider V of X now acting alone. Now, what did we say we can represent the diode if it were small signal analysis? Sabi natin, yung diode natin, we can represent it by its small signal model. And the small signal model is just R sub D. So if I go back to my original circuit, okay, this is now acting alone. So ito naman yung iso-short natin. We short this. This is acting alone. This diode now I replace by R sub D. And this is what I will come up with. Okay. Now, how do I compute for I sub X? Okay. So I'm just going to, yeah. In essence, the solution is, in this particular case, you use phasor analysis. Use phasor analysis. So if you thought walang gamit yung phasor analysis sa electronics, meron din, ano. If you thought that you'll only see phasor analysis again in your electrical engineering courses, well, it still has its uses in electronics. Okay. So if I convert this to its phasor equivalent, if I got the equivalent impedance looking into these terminals, okay, Z equivalent, okay, Z equivalent is equal to R plus R sub D in parallel with Z sub C, where Z sub C is equal to minus J over omega C. omega is equal to 2 pi f, and f here is 1 kilohertz. Where f is equal to 1 kilohertz. Okay. So anyway, what is going to be the phasor I of x? The phasor I of x will just be the phasor V of x divided by Z equivalent. So you just review your, because we're running out of time. You just review your triple E 1, 2, 3. Okay. So this is now my phasor I of x. Okay. This is the phasor V of x, 0.0055 millivolts. We assume it's our reference phasor, so at an angle 0. This is now Z of c minus J 15.92. So this is Z equivalent 50 plus 18.06. Why 18.06? No, I forgot. No? What is R sub D? R sub D is, what did we say it was? Here, no? Use this formula. Eta is equal to 1, so that's just V of t over I sub D. So R sub D is eta V of t over I sub D. So this is 1 multiplied by 0.026 divided by yung kinompute natin dito. Okay. 1.44. Because that is the DC component of your resultant current. Okay. So anyway, so this is the phasor value of I of x, and if you convert that now to time domain, this is what you get. And so finally, this is going to be your expression. Okay. Any questions?
Sir, random lang. Pero saan ba nakuha si 0.120?
Okay. This is supposed to be your RMS value. Okay. But when you have your time domain, this is supposed to be your amplitude. No? So you have I amplitude is equal to the square root of 2 times I RMS. So if I multiply this by the square root of 2, I should get this.
Okay, sir. Thank you po.
Medyo nakakatakot ba na? But this is just one particular problem, no? No, anyway. My point here is I just wanted to show you that, yeah, to analyze this circuit, you can do it by splitting the problem into two. One analyzing the DC component, and the other analyzing the time varying component. So that's all that I wanted to show you. It just so happened that in the analysis of the time varying component, you had to use phasors. That's something you're not going to encounter very often in this course. It's just for this particular problem. Okay, I was going to discuss with you just very shortly, no? I just wanted to go through Zener diodes with you. So give me about 5 minutes to do that. Yeah. The last subtopic under diodes is actually other diode types. Now, most of this material, if you go through the notes, is really very qualitative. No, the discussion of the other diode types. The only thing that was discussed at some length in this particular submodule is the Zener diode. So I just wanted to go through that very quickly with you. So these are your diode VI characteristics. So if I apply a negative voltage across my diode, I'm going to get a very small current. That is my leakage current. At some point, however, this is what's going to happen. So as I increase my negative voltage, at some point, all of a sudden, my characteristic curve is going to go this way. The current, a negative current, a very large current is going to all of a sudden flow. And the voltage at which that happens is going to be almost constant. And this is what we call breakdown. We call this Zener breakdown. Okay, why does the diode break down? Well, there are two possible reasons why a diode breaks down. One is because the electric field is already very strong, because you're applying a very large negative voltage, your covalent bonds just rupture, releasing electron hole pairs. So talagang malakas na yung electric field, no, na yung electrons nahahatak na lang away from the covalent bond and are promoted to the conduction band. And because your voltage is negative, then a negative current will flow. That's one mechanism. The other mechanism is what you call avalanche multiplication. Because you have a very large electric field, the drift current, remember your drift current is reverse saturation current. Because of the very large electric field, you remember that potential here going down, malaking electric field dun sa pagbend ng energy, ano? Your electrons that are drifting will have a very high kinetic energy. When it collides with other electrons, it might impart enough energy, and that those electrons will now be promoted to the conduction band. And there's an avalanche effect, no? As you release more electrons, those electrons will continue to gain kinetic energy, further releasing more electrons, and you get what you call avalanche multiplication. So those are the two reasons why you can have breakdown. Now there's a special type of diode that can operate in this region, because normally, if it's an ordinary diode, you operate in this region, sunog na yung diode mo. But there's a special type that can operate in that region, and you call that a Zener diode. That's designed to operate in the breakdown region. And the nice thing about this region is this line is almost vertical, and therefore you have a constant voltage. So you can use the diode as a voltage regulator. And this is the symbol for your Zener diode. And so your Zener diode actually has three modes of operation. It can operate here in the forward mode, where the voltage across it is approximately equal to V sub F. It can be non-conducting, so it's non-conducting from this point to this point. So the current is approximately equal to 0. And then it can be operating in the Zener mode. So those are the three modes of operation. So here it's just your constant voltage source model in the forward mode. Here, it is just an open circuit. This is in the non-conducting mode. And then here, it is also a constant voltage source model, but this time at the Zener breakdown voltage. And usually, when it is operating in this mode, then we reverse the reference directions for current and voltage. So that's what I'm saying here. The reference voltage polarity and current direction normally opposite that of a normal diode. Okay, so just to give an example, let's say this is my input. And then I have this circuit. Okay, what will be the response of my circuit? Okay, whenever my input voltage is greater than the Zener, well, how do you determine the response? You know? the way you determine the response is you take the diode out. Ito tatanggalin natin. And you get the open circuit voltage. So very similar to an ordinary diode, one way of determining the response is take the diode out, you get the open circuit voltage. So here, if the open circuit voltage is greater than the forward voltage, you know it is conducting. If the open circuit voltage is less than the Zener voltage, you also know it's conducting, but this time in the Zener mode. And when your open circuit voltage is in between the two, you know it is not conducting. So here, whenever V sub in is greater than 5 volts, my output will be 5 volts. So if this is my 5-volt line, whenever V sub in is greater than 5 volts, my output will be 5 volts. So that's here. When V sub in is less than 0.7, so that's this particular condition. When V sub in is less than 0.7, because remember the current now is counterclockwise, no? And my voltage polarity is opposite, no? The normal polarity. So when V sub in is less than 0.7, so let's say this is 5 volts, no? This is 0.7. This will be my output, 0.7. Then in between the two, my input will be equal to my output. Okay, so this is my output. Okay, that's all I have time to explain now, but there's another problem here. There's an explanation of the problem given in the text. So just go through it on your own. No? Don't have time for this problem anymore, but it is quite straightforward. And if you have any questions, you can ask me through Uble, no? or even through email, no? But maybe better through Uble. So I'll stop there. Any questions? So that's all. I will close the session. I have to close the session in about 5 minutes. So I have about 5 minutes for questions if people want to stay on. I will close it in 5 minutes or when the last person leaves, whichever is earlier. Okay. Thank you.
Thank you po, sir.
Thank
Thank
you.
you,
po.
sir.
Yes, sir.
Thank you, sir.
sir.
Okay.